Welcome to The Explainer. You know that little blue dot on your phone's map? Have you ever stopped to think about what's really behind it? Well, today we're going to dive into the incredible physics that make it all possible. And it's a wild ride, from a thought experiment that's centuries old all the way to Einstein's theories of space-time. So where does this whole story begin? Well, it all starts with a really cool idea from Isaac Newton. I want you to picture this. You've got a cannon, and it's on top of a crazy high mountain. You fire a cannonball, and of course, gravity does its thing and pulls it right back down to Earth. Seems simple enough, right? Okay, but what happens if we pack in some more gunpowder? The cannonball shoots out faster, right? And it goes way farther before it finally hits the ground. And here's the key part. With every bit of extra speed, the path of that cannonball starts to curve more and more, following the curve of the Earth itself. So if you could fire it at exactly the right speed, something amazing happens. The curve of its fall perfectly, and I mean perfectly, matches the curve of the Earth. It's still falling, yeah, but it never actually gets any closer to the ground. It just keeps going. And that is what we call orbital velocity. It's basically a state of continuous, endless freefall. And this is the secret sauce right here. Getting into orbit isn't about escaping gravity, not at all. It's actually about using it. You're not trying to go up. You're trying to go sideways so unbelievably fast that you just keep missing the ground. That's it. That's the big secret behind every single satellite we've ever put up there. Okay, so that's the thought experiment. But let's get real for a second. What's the actual number? How fast is fast enough to pull this off and find that perfect balance between shooting forward and falling down? Get ready for this. The magic number is about 8 kilometers per second. Let me say that again. 8 kilometers a second. That's almost 29,000 kilometers an hour. To put that in perspective, at that speed, for every 8 kilometers you fly forward, the Earth's surface curves down by about 5 meters. And guess what? That's the exact same distance gravity has pulled you down. It's a perfect match. Right? So staying around the Earth is one thing. But what if circling isn't enough? What if you want to, break free, head out to Mars, or even further? Well, for that, you've got to go even faster. You need to hit what we call escape velocity. And that number? A whopping 11.2 kilometers per second. Once you hit that speed, Earth's gravity just can't hold on to you anymore. You're not just missing the planet at this point, you're saying goodbye for good. Okay, so we've got these cosmic speed limits. How do we actually use them? Let's dive into the invisible tech that pretty much runs our modern world, starting with some satellites that look like they're not even moving. Yeah, one of the absolute coolest applications of all this is the geostationary satellite. If you look up at the sky, one of these things looks like it's just stuck in one spot, totally motionless. And that's super useful for things like your TV signal or for keeping an eye on the weather. But of course, it's not motionless at all. It's moving incredibly fast. To pull off this trick, a satellite has to follow a very, very specific recipe. First, it has to orbit right over the equator. Second, that orbit has to be a perfect circle, no ovals allowed. And third, this is the big one, it has to finish one full lap around the Earth in exactly 24 hours, the same amount of time it takes the Earth to spin once on its axis. And this just shows you how precise this all has to be. To get that perfect 24-hour lap time, the satellite has to be at an exact altitude, 36,000 kilometers up. If it's even a little bit higher or a little bit lower, the whole illusion just falls apart. All right, let's bring this all back down to Earth and right into your pocket. How does this whole network of satellites, all zipping around at insane speeds, figure out exactly where you are? You see, the Global Positioning System, GPS, it's not just one thing. It's actually this huge interconnected system. Think of it like a three-part harmony, with all the pieces working together perfectly just to create that one little blue dot on your screen. So part one is the space segment. That's a whole constellation of at least 24 satellites always orbiting the Earth. Part two is the control segment. These are the command centers back on the ground, keeping an eye on the satellites, making sure they're healthy and where they're supposed to be. And finally, there's the user segment. And that's you. It's your phone, your car, whatever device you have that's listening for those signals. So here's a really important distinction. Your phone isn't being tracked by these satellites. It's the other way around. Your phone is a receiver. It's just listening. And the method it uses to figure out where it is, well, it's just some really clever geometry called trilateration. So how does that work? Okay, imagine this. Your phone picks up a signal from one satellite. That signal basically says, okay, you are somewhere on the surface of this giant sphere. Not super helpful yet. But then, it gets a signal from a second satellite. Now your location is narrowed down to the circle where those two spheres overlap. Getting warmer. A third satellite signal narrows it down to just two possible points. And since one of those points is usually, in outer space or moving at the speed of a jet, your phone can pretty easily figure out which one is you. But to get really, really precise, your phone grabs a signal from a fourth satellite. This does two things. It locks in your location for sure, but it also does something even more important. It corrects for any tiny, tiny errors in your phone's own clock. And that's what gives you that incredible pinpoint accuracy. But hold on, there is one last piece to this puzzle. And honestly, it's the most mind-blowing part of the whole thing. Because without it, the entire GPS system we rely on would be completely useless in a matter of hours. And it all comes down to one person, Albert Einstein. And I am not exaggerating. For GPS to work at all, it has to constantly account for Einstein's theories of special and general relativity. Yeah, we're talking about how time and space literally bend and warp. So here's the crazy situation those satellite clocks are in. Because of general relativity, the weaker gravity up in orbit means their clocks actually tick a tiny bit faster than our clocks down here on Earth. But at the same time, because of special relativity, the fact that they're moving so fast means their clocks also tick a tiny bit slower. It's a constant cosmic tug of war. So which one wins? Well, it turns out the faster effect from weaker gravity is just a little bit stronger. The end result is that the satellite clocks gain about 38 microseconds every single day. Now that sounds like nothing, right? 38 millionths of a second. But GPS needs timing that's accurate down to the nanosecond. If engineers didn't correct for this time warp, your GPS location would be off by about 10 kilometers. Every single day, your map would be totally useless. So the next time you pull out your phone and see that little blue dot, just take a second to think about everything that goes into it. Remember Newton's cannonball, falling forever but never landing? Think about that cosmic dance of geometry pinpointing you from space. And don't forget the beautiful, weird way that time itself has to be bent just to make it all work. It really makes you wonder, right? What other incredible physics are hiding in plain sight all around us?